This is video 9 on the practice of orthokeratology with your Medmont E300 corneal topographer. Start with 4 quality baseline maps and highlight those 4 maps on the database side, and then analyze them for quality. Look at the 4 of these images. Do you see any one map that looks like it should be thrown out, or multiple maps that look like they're poor? In this case, map number 4 has a fairly low upper lid that's crossing a fair deal of the upper iris, and the eyelash shadows are coming down and blocking some of the ring reflection. This gives us some false areas of flatness. 3 areas here that I think are of concern. If you look at maps number 2 and 3, they also show some missing information in this superior area, which may be the result of long eyelash shadows, where map number 1 appears to be the best image of the bunch. So map number 4 should definitely be unselected from our calculation. We could also look at the apical curvature. By clicking our cursor in the center of the topography, you can see we're 46.1, 46.3, 46.4, and 45.9 as central curvature. This map appears to be the flattest. These 2 appear to be the steepest. So this map appears different from the others in appearance and also in central radius of curvature. Let's unselect it by holding down the Control key and clicking on it in the database. Now we have the balance of our 3 maps, and we can analyze which should be our best map to calculate our baseline initial orthokeratology lens. We also want to know which map will be best for doing comparisons when the patient has worn the lens. So let's look at the balance of the 3, and it appears map number 1 has the most corneal coverage and appears to be the smoothest contours. So we'll highlight number 1 from the database. Let's determine the candidacy for ortho-K. First, the patient has a fairly steep cornea, 45.9 as flat K. When we click our cursor in the center, we read 46.1 as an apical radius. We know that steeper corneas respond best to orthokeratology as compared to flat corneas. Secondly, we know that high eccentricity eyes tend to respond better to orthokeratology than low eccentricity eyes. Normal eccentricity is 0.65. This patient measures 0.79. So we know that this patient is a better than average candidate for orthokeratology. Now, is this eye too astigmatic to be fit with a symmetrical orthokeratology lens? We wouldn't expect so with virtually nil for corneal astigmatism, only 0.1 of a diopter corneal sill in this very spherical cornea. But if we were dealing with an astigmatic eye and we weren't sure, we could click on Analysis and Details. Then set your chord value for the diameter of bearing of your orthokeratology lens. In other words, at what diameter along your orthokeratology lens will it land on the eye? And we measure sea level, or the height of the cornea, from that point. If you click on the flat meridian, we can read the sagittal depth along the flat at 1591. Along the steep, we measure 1608. The difference between our flat meridian in height and steep meridian in height is approximately 17 microns, which is a very small amount. The threshold where a toric lens is generally required in orthokeratology is in excess of 50 microns. This patient is much lower than that 50 micron threshold between the depth of the eye horizontally or along the flat and the depth of the eye vertically along the steep. So therefore, a symmetrical orthokeratology lens should work quite well. Now let's send the patient home with the lens and analyze the post-treatment response. We select our best baseline map, then our post-orthokeratology or post-treatment map. This is where we use the subtractive map function or the comparison map. Click on the icon that looks like 3 topographies on the same button, and that brings up your subtractive map. A subtractive map takes an older point in time and compares it to a more recent point in time and gives you a difference. Wherever you see blue, the cornea has flattened between this visit and this visit. Wherever you see red, the cornea has steepened between this visit and this visit. So blue would be an area of flattening or reduction in myopia within the pupil. Red would be an area of steepening, in this case well outside of the pupil, so it wouldn't affect vision in an adverse way. We start by clicking on Display and selecting our Axial Power Map. An Axial Power Map tells you 2 very important things. Number 1, the refractive change. When we click our cursor in the center, we can see this patient has a 0.9 diopter effect. If I click the cursor in the lighter area of blue, only a half diopter effect, and up to a 1.4 diopter effect in this deeper blue area. We can also see that the treatment zone, the blue area of flattening, looks very well centered to our pupil margin. If your cursor is clicked in the center, the pupil will appear as black. If you click your cursor on the pupil, it will light up in pink. You can see that the blue area of flattening appears to go beyond the pupil margin 360 degrees. And it also appears very parallel to the pupil. So this is what's appearing to be a very well-centered response. Although the center has a fairly inconsistent effect within the pupillary zone, which is typical of a one-night orthokeratology effect. We next would use the tangential power map, and tangential tells you the position of the lens in the closed eye environment. With axial maps, you look at the center, the blue area of flattening. With tangential, you ignore the center and look at the mid-periphery. Look at the red rings and blue rings just paracentral to the apex. The red ring is where your reservoir of tear is on your orthokeratology lens, creating the greatest suction force. That effectively steepens the cornea up. If this red ring runs parallel to our pupil margin, then we know our orthokeratology lens was well centered while the patient was sleeping in the closed eye environment. We can also look at the blue ring. This is the area where the lens lands on the eye and creates a compressive point. If both the red ring and the blue ring are well centered to the pupil, we know our orthokeratology lens is well centered overnight. The last map you might use is the refractive power map. The refractive power map is very effective for measuring the treatment zone size. If you take your cursor and drag it to the point where the power difference reaches 0, at this value here, that's the limit of the treatment zone. If that 0 point, or that point where the pre and post cornea show 0 change, that will be the limit of your treatment zone. And if it's beyond the pupil margin, you could expect the patient to have a limited, if any, amount of aberrations or flare and glare from overnight orthokeratology. You also note the refractive power map looks very similar to the axial subtraction map in the position of the treatment zone and the refractive change. You could also look at the refractive power map with the post-treatment exam alone and determine if the effect appears to be fairly spherical. Are you sphericalizing the pupillary zone, pushing any astigmatism out of the way, and placing the treatment zone where you would like it? If we go back to an axial map, we can observe this patient after 3 consecutive nights of wear by unselecting, holding down the control key, and unchecking the 1-day map and selecting the 3-day map. And in this case, our axial map is showing us a treatment zone that's filling in nicely. We are now up to 2.9 diopters Rx change. This concludes video 9 on the practice of orthokeratology with your Medmont E300 corneal topographer.